Let's look at a very important principle, Couchy principle of sequence convergence. So a sequence A sub n of real numbers is called a Couchy sequence if for every epsilon greater than 0, there exists p in natural numbers such that the distance between A sub n and A sub m is less than epsilon for all n comma m greater than or equal to p. That is, beyond some index, any two terms of the sequence, no matter how far apart their indices are arbitrarily close to each other. So now we have a Couchy criterion in real numbers. It says a sequence of real numbers converges if and only if it is a Couchy sequence. So statement for that is the sequence A sub n is a Couchy sequence if for every epsilon greater than 0, there exists m in natural numbers such that the distance between A sub n and any other later term is less than epsilon for all n greater than or equal to m and for all p in natural numbers. So what this criterion says is that if we have a convergent sequence A sub n where an is in R, that is real numbers, implies and is implied by A sub n being a Couchy sequence. So if it is a convergent sequence, then it's a Couchy sequence. If it is a Couchy sequence, it is a convergent sequence. Now let's look at example to understand this. A sub n plus 1 is equal to 1 by 2 times A sub n plus 2 by A sub n, where n is in natural numbers. So this is a sequence. Remember, in a previous session, we saw this sequence. And here the beauty is that the first term we choose, second term onwards, this formula generates it. Okay, so this sequence converges to root 2. If we go far enough along the sequence, then all the terms cluster together, no matter how far apart their indices are. So let's look at it graphically. So this is our graph for this sequence. Here you will notice that the first term we have taken is 4. We can take any 3. We can take any value for the first term. It will always converge to a line on the graph. That is nothing but y is equal to square root of 2. Now, this is one way of representing the sequence. Another way is we don't bother with the indices. We just plot the values of the terms. So let's do that. This is the terms of the sequence. Now here again, if you notice, this is the first term 5, 5. Second term 2 point something. This is again 2 point something, and so on. Now this is also converging to a point. This point is root 2. Or rather, x equal to root 2 is this line. Now, that is for sufficiently large n, the distance between A sub n and a term which is much later in the sequence is small for every p in n. Now, let me just zoom in because it looks as if, there is only one point here. So let's zoom in. See here, now it has become 2 points. If I keep zooming in, points seem to emerge from this point. So that is what is meant by clustering together. There are infinite number of points which keep getting closer and closer to root 2. So hence, any two terms taken sufficiently far along the sequence are close to each other. And therefore, the sequence is a Cauchy sequence. We can look at the values also. As we keep going along the sequence, arbitrarily distant terms will be close to each other. That was one example. Now let's look at another example. Second example is our favorite. A sub n is equal to 1 by n. And now let's plot 1 by n. Now again, let me put it on the different form. Again, you will notice that it keeps getting closer and closer to 0. So here, absolute value of a sub n plus p minus a sub n is equal to the absolute value of 1 by n plus p minus 1 by n is equal to, simplify, n minus n plus p by n times n plus p, which gives us p by n times n plus p, which gives us p by n square plus np. Since p is greater than or equal to 1 and n plus p is greater than or equal to n, of course, this implies this, which implies p by n times n plus p is less than or equal to p by np. How can we say that? Because from here, we have removed n square from the denominator. Since we have removed n square from the denominator, that means the denominator has become smaller. That means the entire expression has become greater. Since this has become greater, that means this has become smaller with respect to this. So that is how we can say that p by n times n plus p is less than or equal to p by np. pp, if we cancel it, we get 1 by n. So for any epsilon greater than 0, let's choose n greater than 1 by epsilon. Then for all n greater than n and all p in natural numbers, we would have the distance between a sub n and a sub n plus p is less than or equal to 1 by n, which is in turn less than epsilon. All this basically means is that if we take a sufficiently large n, say 1000, then all the pairs a sub 1000 plus p, comma a sub 1000 must be close to each other. When we say sufficiently large n, means what? It depends on the sequence. Some sequences converge very fast. Some will converge slowly. So depending on whether it is a fast converging sequence or a slowly converging sequence, we will have a sufficiently large n. And that also means any sequence which oscillates while converging to a limit is also a Cauchy sequence, because the absolute value takes care of the signs. And let's look at this. A sub n is equal to minus 1 to the power of n divided by n is also a Cauchy sequence. Let's plot it. We have, so when it is 1 for the first term, it will be minus 1 to the power of 1 by 1, which gives us minus 1. For the second term, minus 1 square by n, that is 2. Minus 1 square is 1, n is 2, so 1 by 2. If we look at it in this form, then we have convergence. This is also a Cauchy sequence. Again, let's zoom in to see it better. The reason it stops suddenly here itself is because n is not yet large enough. As I keep increasing n, it will get closer and closer to 0. That was Cauchy principle of sequence convergence. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.